Hello, I'm Roman and welcome back to the series of the videos Let's Learn Neural Networks from Scratch in Go, where we dive into the bare bones of the neural networks using the book called Neural Networks from Scratch in Python. But as you can guess, we're not using Python here, we will use Golang. And in a previous video, we went through the page of, well, we're still on the chapter 4 called coding our first neuron. And in the previous video, we used GoNum to replicate the code that is written with NumPy here. So that was the result. And the last thing we need to do here, so we were able to use matrix product function from the GoNum, and what we need to do, at least what I will start to do, there is still a chapter, a layer of neurons and batch, where we need to use batch processing, and I want to replicate in a GoNum. This is the leftover of this chapter, so we'll start from this, and then we will go to the third chapter. So let's go. We checked yesterday that the idea of the batch processing is to use several inputs at the same time for the same neurons. For example, here we have the first input, the second, and the third. And the thing that in order to use matrix product, we need to transpose weights matrix, and then we can use matrix product, and we'll get the result. So for example, this will be our input, this will be our first neuron, second, third, and this will be the output for the first input, for the second, and for the third. And we can actually think about this input as the output from the previous layer. But I think this is the goal of this. And in the end, we will need to do the matrix product of these two matrices. We will need to add the biases, and this will be our result. For example, we can see that for the first input that we code before in the run model, this is the result. So let's try. This is the code with the NumPy. It uses the inputs, which is a two-dimensional array. It uses the second array weights, which is again two-dimensional array of the weights. And you can see that in order to use dot product, we take the inputs, we take the weights, we transpose them, and then we add biases. And this should be our result. Let's build it and go. But before, okay, let me check something. Yes, I'm recording. But before, I want to do some cleanups. First, I don't need the dot product function anymore because we will use it from the GoNum. Second, okay, I will leave this stuff for now just for me, but this is what I'm going to do. I need to create an array of arrays. Interesting how it will look like in Go. I guess it will be like this. Okay. So this is the first input. This is the second one. And this is the third one. Okay, first, second, and third. Okay. And right now we have 3 neurons, and we need to create the matrix weights, right? This should be again 2-dimensional, and it will take weights from the first neuron, weights from the second, and weights from the third, right? And biases. That will be 1-dimensional array. Okay. We don't need it. Okay, in order to use GoNum, we need to create 2 dances, right? The first one should be, well, actually 3. But I believe we should have something like matrix summary. It's sum. Sum returns the sum of the elements. No. No, I need the element-wise summary. Interesting. So it looks like okay. I'll try to do this later. Okay. So what I need to do? Inputs. Dance. That should be math. New. You can create Vexim to just okay. We have 3 rows. We have 4 columns, and our data is inputs. Oh, okay, so it always takes the 1-dimensional array and then it will split it into 2. Okay, makes sense. So this is what we're going. So this is the first, second, and third, right? Okay. With weights, I think this. Okay, let's create an empty. Then wait. Can I append? cannot use weights as float. Okay, but can I? Not the new. Yeah, but I want to. I mean, there is another slice, right? Copy the copy into destination, but I want to append. So you cannot append. I don't believe it. And append. As a special case, it's legal to append a string to a byte slice like this. Appends elements to the end of the slice. It has sufficient capacity destination is provided. It does not a new underline array. Append returns the updated slice. Slice is therefore necessary to store the result of append. Yeah, but why I cannot append another slice? Okay. Weight ends, and I need bias as dense. It will have one row, 3 elements. Okay, let's replicate. I wrote it in this way just for me, for better visualization. So we have weights where we append first neuron, second, third. We have the input dense, we have the weight dense, and we need to transpose it. And this is a tricky one because it will create. Okay, I can print. I can print math. We should have inputs. Wait. And biases, right? Okay, I don't need this anymore. Okay, let's compare. We should compare it with this one because I already transposed 1 to 3 to minus. Okay, inputs. Okay, weights. Okay, we have the transposed weights and we have the biases. Okay. Right now, the $1,000,000 question, how to use the matrix product. So we should have output, right? And the output will be Okay, we need to create the new modes. Oh, math product. It will be. Okay, then there is a question. And ideally, I should take it from. So the output then should have the same dimension as the input one. So ideally, I should done this input tens dims C and data nil. Okay. It's actually a shame that I cannot do like this. Okay. And then maths product, no inverse. We need to use product and input dense weights. We should have results without biases. Where is it? Okay, we should have this one, right? Okay, let me guess. Dimension mismatch. Wait. Okay, wait. Oh. Okay. 1, 2, 3. Oh, 3. So it's actually 3 by 3, but the 3 should come from the transposed columns. Yeah. Yeah, I took the wrong assumption, so it will have. Okay, so I have. Okay, for one input, I have 3 neurons. So it means that. Okay, so even. Okay, so I had 4 inputs, but I have 4 input values. I have 4 weights, but I have 4. Oh, I have 4 weights from each input to one neuron, but I have 3 neurons. So this is why I will have 3 output from each neuron. And since I have 3 batches, this is why I end up 3 by 3. Right? Right. Am I right? Right. And yeah, it looks correct. Then I need to do. Looks like I have to do it manually, right? I mean, the results still. Um, mm, can I do something like this? Mat product plus bias. Invalid operation. Operator plus not defined on the mat product variable of type mat tense. Okay. Okay, so. Okay, let's use as the result because we will add Can I modify the row? What I feel float 64. Okay. Raw matrix returns the underline used by the receiver. Changes to the elements in the receiver following the call will be reflected in return plus 64 general. Okay, the question, can I do something like this? Cannot index. Okay. Can I add? Okay, returns. But it returns. How I can change it? Set Marshall binary. Can I set the element at? Okay. Okay. So what we need to do? We need to go through all of the rows. And add. So right now we need to add biases. Actually, I'm not sure because the underline, I mean, rows, calls. Let's do it like this. Result team. Because I'm not sure. I mean, the underline. I mean, the underline matrix should be a one-dimensional. Even if we treat it as a two-dimensional, the inside it's a one-dimensional. So so we take in the value from right. Then we add biases at 0. No. J. Then we result set right. Right. As you can see, our neural network takes in a group of samples and outputs a group of predictions. If you have used any of the deep learning libraries, this is why you pass in a list of inputs, even if it's just one feature set, and are returned as a list of predictions even if there is only one prediction. Chapter supplementary material, chapter code for the resources. Sample code. Okay, so to sum up, we finished with the coding of our first neuron, and actually we end up doing input batches. Okay. Chapter 3. Okay, it's half of an hour. Let's go. The neural network we've built is becoming more respectable, but at the moment we have only one layer, which is true. So this is our 3 neurons is just one layer. Neural networks become deep when they have 2 or more hidden layers, and actually the output, well, this is the result, this is the output. So I mean, it's actually interesting. Is it the hidden layer that we created, or it's actually just the output? Because we have the input, we have the neurons, and each neuron has the output. So it looks like we just have the input and the output. Neural networks become deep when they have 2 or more hidden layers. At the moment we have just one layer, which is, okay, effectively an output layer. Why 1, 2 or more hidden layers will become apparent in later chapter. Okay. Currently we have no hidden layers. A hidden layer isn't an input or output layer. As the scientists, you see data as they are handed to the input layer and the resulting data from the output layer. Okay. Layers between these endpoints have values that we don't necessarily deal with, hence the name hidden. Okay, so the main difference that they kind of temporary steps between the input and the output, and the hidden, because we as I would say users of the model, we don't deal with them directly. They will be somewhere inside the model, and we deal with the inputs and then we grab the output. So that's it. We don't deal with these intermediate layers. Don't let this name convince you that you can't access these values though. We'll often use them to diagnose issues or improve your neural networks. To explore this concept, let's add another layer to this neural network. And for now, let's assume these 2 layers that we're going to have will be hidden. And we just have not coded an output layer yet. To explore these concepts, let's add another layer to this neural network. And for now, let's assume that these 2 layers that we're going to have will be hidden layers. Okay, so we assume that this is the first layer, and we'll add the second one, and we just don't have the output. Okay. Before we add another layer, let's think about what will be coming. In the case of the first layer, we can see that we have an input with 4 features. That's right. 1, 2, 3, 4. And we have 3 neurons. Okay, so the number of weights, so we have 1, 2, 3, 4, corresponds to the number of the nodes on the previous layer, which makes sense. And the number of neurons defines the number of the inputs for the next step. So for example, imagine that we'll have this here, the 5 neurons, okay? It will mean that we will have 5 neurons with three weights, because for example, first neuron 1, 2, 3, second neuron 1, 2, 3, and again and again. Okay. Samples feature set data get fed through the input, which doesn't change it in any way to our first hidden layer, which we can see has 3 sets of weights with 4 values each. 3 sets of the weights, right? 1 set, first, second, third, with 4 values each. And 4 values because we have 4 outputs on the previous layer. I will think about this as just another hidden layer, because what we'll see, like, you know, any layer will become the next input for the next layer. Each of those 3 unique weight sets is associated with its distinct neuron. Each of the 3 unique weights sets is associated with, yes, those. Since we have 3 weight sets, we have 3 neurons. Okay, in the first hidden layer, each neuron has a unique set of the weights, of which we have 4, as there are 4 inputs to this layer, which is why our initial weights have shape of 3 or 4. So yeah, okay. Number of rows, not transposed one, just to declare. Number of rows defines the number of the neurons. Number of columns defines the number of the previous neurons. I would just go with like this. So if the next layer should have 3 neurons, okay, each neuron will have the number, each neuron will have number of weights that is equal to number of the neurons in the previous layer. So for example, just for me, rows defines number of neurons for a layer. Calls defines number of inputs / number of neurons from previous layer. Now I wish to add another layer. To do this, we must make sure that the expected input to that layer matches the previous layer's output. This is what I've been talking. We have set the number of neurons in a layer by... We have set the number of neurons in the layer by setting how many weight sets and biases we have. The previous layer's influence on weight sets for the current layer is that each weight set needs to have a separate weight per input. This means a distinct weight per neuron from the previous layer of each we're talking about the input. The previous layer had 3 weight sets and 3 biases. So we know that it has 3 neurons. This means for the next layer we can have as many weight sets as we want, because this is how many neurons this new layer will have. But each of those weight sets must have 3 discrete weights. I didn't understand the thing, but okay. Let's just go through the code. To create this new layer, we're going to copy and paste our weights and biases to weights and biases 2 and change their values to new made up sets. This is an example. Okay. So this is the first layer. This is the second layer. Next, we'll call our outputs layer 1 outputs. So layer 1 outputs takes the inputs, takes the first weights, takes the matrix product, and then biases. As previously stated, inputs to layers are either inputs from the actual dataset you're training with or output from the previous layer. This is why we define two versions of the weights and biases, but only one of inputs, because the inputs for the layer 2 will be the output from the previous layer. Okay, yeah, this is what we see. And again, to calculate the outputs for the second layer, we take in the matrix product. We calculate the matrix product between the previous outputs, transposed weights for the second layer, and we add in the second biases. So this is all together. Import the, this is the input, this is the first, this is the second. At this point, our neural network could be visually represented as this. Okay, so this is what we go into code. For now, I think I'm recording already 40 minutes, right? So what I will do, I will clean up the code a little bit, and then we will continue with this implementation in the next series. So, okay. What I can do. Oh, I guess I can declare it. So this is not the weights. I mean, ideally, I would create something like not the neuron structs, maybe type layer, actually, right? And what we'll have? We'll have weights as dense, biases as another dense. Okay. Then okay. Then I want to layer layer Math new dense. Okay, we have 3, we have 4, we have nil, and we have new dense 1, 3, nil. Then the question, can I example weights adds an A and B element twice, place in the result. It will panic if two matrices. Oh. Okay, so at this moment, looks like I need to really missing. Oh, okay. Mm. Mm. I'm thinking how I can add. Ah, but okay. I will just take the. It's 2, 3, 1, and okay. Okay, this is the first. This is the second, and third. And so right now I should have layer 1 weights and layer 1 biases, right? So here, layer 1 weights, layer 1 weights. Here, biases. No. Layer 1 bias. No. Okay, so it's actually on. input. Result. Oh, right, because oh, okay. But for I mean, I can store it as transposed. Right? Or I can store it as it is, but then use it only like this. Cannot take the address of players. Okay. Okay, let's store it as matrix. Will it work? New dance. Cannot interact, make dance. Okay. Let's check what we had. That should be from the previous one, right? So, okay. So, biases, then we take in, I don't need this, results. So this is actually the multiplication. Well, I mean, this is actually the path through one of the layers. So I think I should. Okay, the next thing I want to do, and I will start from the next one. Move to so take input, take layer, output, new input. Right? Because the result, what is the result? The result is the input for the next layer. So we can move this to another function. So we can do something like this. Layer 1 output, like calculate, pass inputs and pass the layer. Then we have the output, then we can take this output, call this function the second time, we'll have the layer 2 output, and again, we'll take the output from the previous call, take the next layer, and we will have the result. So we will start the next series from moving this into the function and implementation of this. And then what's next? Training data. And then we will dive into new. I think this is, we will just study, then layer class. Okay, and then I think then we will implement some activation function and actual output layer. But for now, thank you for watching, and I see you in the next video. And by the way, don't forget to check my main channel. I'm talking about way more things. Bye bye.